Good afternoon, everybody. So welcome to session 3 entitled Building Facade. My name is Shadi Najjar. I will be co-chairing this session with Mr. Ziad Haddad. I am a faculty member in the Department of Civil and Environmental Engineering. So we have 4 presentations in this session. 2 of them will be physical and 2 online. And I would like to welcome you, and I will give the stage to Mr. Ziad to introduce the first speaker. Recorded. Ziad.
Thank you, Dr. Shadi, and I take the opportunity to thank Ashray, Dr. Ghaddar for organizing all this marvelous event, taking care of it, to thank Sandrine and everyone who helped preparing it, and to welcome you all on behalf of Ashray. Very interesting session today, mostly about the building envelope. So before I start, I just want to, not to misintroduce myself, Dr. Samir Trabulsi, President. Ahla wa sahla fik bi baytak. It's very good to see all the good friends again and again, since we're getting back to live. Making all these encounters more interesting. So the building envelopes is something super interesting. I'd like to call it our third skin. So after our own skin, our clothing, then since we humans stopped being nomads and went sedentary and start building homes, etc., we were on a trend to more and more live indoors until we reached a point whereby we're spending maybe 90% of our 24 hours indoors, making the building envelope something very important conceptually for a sustainable building. We have a great selection of top speakers. I'm going to start with my colleague, presenting him, Mr. Mohamed Hmadi, with his presentation on phase-changing material integrated in the buildings, and a case study from Lebanon, very interesting. So Dr. Hmadi has a PhD in renewable energy from both the Doctoral School of Science and Technology, EDST, the Lebanese University, which we're proud of, and the Higher School of Engineers of AUB, of Beirut, OZIB, which is the St. Joseph University. He's a mechanical engineer with more than 5 years of experience in HVAC, public health, and firefighting design and consultancy services in the building construction sector. He has participated in international conferences and has publications in scientific journals. He got the title of Certified Energy Manager from the Association of Energy Engineers, which we had the pleasure to accompany each other in that journey, and the Leadership in Energy Efficiency Design, LEED GA, from the US Green Building Council. Please join me in welcoming Dr. Hmadi.
Thank you very much. Good afternoon. In this presentation, we are going to investigate the performance of adopting hot and cold phase change materials towards reaching a near-zero thermal energy residential building in Lebanon. So the way we are using our global natural resources in order to provide the high increased demand in energy consumption is increasing the CO2 emissions. This increase in CO2 levels is polluting our environment, endangering our survival, and polluting our nature. And based on the fact that buildings are responsible for more than 70% of energy consumptions, so many researches have been conducted towards providing the thermal loads of these buildings from solar renewable sources. But what are the challenges facing these researchers? First of all is the peak chiller capacities. You know that most of the consultants, when designing their buildings, they choose to have the capacity of the chiller based on the peak load. Where this peak load only occurs for 1% all over the year, this increases its capital cost and also increases its operational one, due that chillers are working most of the time on the partial loads, which has lower efficiency. Secondly, the high supply temperature by using concentrated solar panels, which needs high specification materials and thus increases the capital cost. Thirdly, is the high storage volumes, which is deterring from reaching the 100% solar fraction, and so we still need an auxiliary source of energy in order to get thermal needs all over the year. All of these factors is increasing the payback period of the systems and making most of these systems unfeasible. From here, the idea was flourished towards developing a solar thermal system which could solve all of these challenges. We will provide the sequence of operation and the optimization algorithm, starting from the conventional building components baseline scenario, then adopting energy conservation and efficiency strategies, reaching a low energy building, and then finding the simulation results, the capacity factors, and the feasibility study, reaching, of course, a near zero thermal residential. So let's start first with the solar thermal system. This system consists firstly with the absorption chiller, lithium bromide absorption chiller, which would provide the chilled water need for the building. Evacuated tube solar collectors to provide the heating, domestic hot water, and the generating power for the chiller. We have the hot phase change material, which will meet the fluctuations between the solar irradiance and the demand of thermal needs. And we will have the cold phase change material, which will give us the opportunity for the absorption chiller to work on a full capacity for a specific amount of hours during the day in the load shifting, or to work all over the day in a 24-hour scenario. So if the energy produced by the absorption chiller during the peak power is greater than that needed, this excess and chilled water energy will be stored inside the cold phase change material, else it will be discharged and we will get our energy need from the cold PCM. So how the system operates? First of all, if the sun shows up after a long non-solar period, then the circulator, hot water circulator pump will start circulating the water inside the evacuated tube until the temperature of supply has been reached. When T1 is reached, which is less than 100 degrees, the evacuated tube will start providing the system with the needed thermal energies and also the energy needed for the absorption chiller. Now, if the energy collected from the solar collectors is greater than that needed, then the excess of this energy will be stored inside the hot phase change material. And on the other hand, if the energy needed is greater than that could be collected, then the PCM, hot PCM, will interfere to maintain the stability in the system and will provide this deficiency in energies. Of course, if there is no solar radiation, the hot PCM only will run the system. Now let's move towards the conventional baseline scenario. So we choose Beirut, the capital of Lebanon, as our case study. Beirut is characterized by a moderate temperature. We have high solar irradiance. We have more than 300 solar days, which makes any solar thermal system a good choice. Also, everybody knows that we are passing through an economic crisis. Everybody is going towards renewable sources of energies in order to provide their needs. This makes the solar, or this makes our case study a very perfect place. So our building will be a 4-floor building. It is designed based on the thermal standard of Lebanon. Now, moving towards the energy efficiency and energy conservation strategies. First of all, we have enhanced the walls, roof, and windows U values, provided an external shading for all windows, provided a double roof to maintain more area for the thermal panels and to provide shading for the last floor. Also changing the set point and setback temperatures of the system, introducing heat recovery wheels and economizer modes. Using a parametric study, combining all of these energy conservation and efficiency shows that we can reduce up to 36% in the cooling need and more than 21% in the hot water needs. Now moving back to our simulations. So having the hour by hour domestic hot water heating and cooling loads, we have calculated the amount of hot water needed and chilled water needed. Then using the absorption chiller combined with the cold phase change material, we have found the hourly hot water needed for this building. On the other hand, we have the solar irradiances and we have the evacuated tubes. So the evacuated tube will provide either directly to the hot water needed or to the hot PCM, which will both maintain the stability of the system. Now, in order to size or to find the capacities of these four components, we used the Hook and Jeeves optimization algorithm, taking into consideration that this system could work for the whole year without the need of any auxiliary source of energy and having the combination with the lowest capital cost. Results shows that the load leveling and load shifting both are very good for running the system all over the year without the needing of any auxiliary source of energies. We have found the capacities of the different components and the CO2 emissions reaching an energy use index of 9.5 kilowatt hour per meter square per year. Using the feasibility study and taking into consideration the real price of electricity, since in Lebanon the electricity is muchly subsidized, taking the official rate of the generators as the running cost for the electricity, we have the feasibility of the system of around 6 years. Now, as a conclusion, this presentation or this work could act as a baseline for the future designers. Whenever they design their work, they take into consideration the energy efficiency and conservation studies, which proven to reduce more than 60% of the amount of life cycle amount of a system compared to a building with a conventional thermal envelope. And this system have provided more than 90%, reduced more than 90% of the CO2 emissions, electrical bills, and energy consumption. Taking into consideration the evacuated tube, which has a lower temperature supply, it has reduced more than 38% if compared to a system with using concentrated solar panels. Using the PCM, the phase change material, has reduced the volume of the storage by more than 8.9 times. And finally, this system could reach 100% solar fraction, reducing or enhancing the efficiency by more than 30%. Thank you very much.
Thank you so much for your presentation, Dr. Hmadi. Very interesting, highlighting the importance of storage. You all know energy storage is not like an efficiency measure. It's not renewable, but we have to do it in order to shift or level the loads or to benefit from the different rates of energy supply at different times. And phase change material is one of those interesting things. Good point for consideration. We'll take questions from the audience, please. Yes, Martine.
Thank you for the presentation. I just want to highlight for the savings, when you mentioned the 92.6% savings on the electrical bills, you mean from the PCM integrated with the chiller with the solar? It's all, this rate or this percentage, it is practical أو هي بس إنه theoretical study كانت يعني?
No, we haven't done an experimental study about that. It was using a simulation and the feasibility study of the whole system, using all the energy conservation measures, energy efficiencies, using the chillers, the evacuated tube as a system.
Okay.
We run the operation, we found the operation or the energy needed, electrical energy needed for this system compared to the conventional one, using the normal DX units as a system without any energy conservation and efficiency, a normal ordinary building, and we get and we get the life cycle cost, and we get this.
Okay, no, it's clear. لأنه 92.6%. I said it's very high, but no, it's clear. Thanks.
Yes, thank you.
Thank you, Martin. We have the time to take more questions. Okay, in the meantime, so I've noticed, Dr. Hmadi, that you have done several measures in order to reach the high savings or the 6 years payback, which is still challenging with the rates. And I guess the technology has to get a little bit cheaper with the time so that it becomes more and more feasible. And I noticed, just for everybody's consideration, that one of the main elements was changing the set points of cooling and heating. I'd like you to emphasize on that, which is not to the merit of the system, but to a behavioral change, shifting us from very comfortable indoors to maybe more rational indoors. Would you like to highlight on that, please?
Exactly. Changing the set point temperature, for example, in summer, all of us in our offices, in our rooms, we set the X unit or the HVAC system towards 16 degrees. But this degree will never be reached. We reached around 20 degrees, for example. But for the thermal comfort, it is between 20 and 25 degrees, according to ASHRAE 55. So increasing this, the HVAC set point temperature, for example, to 1 degree or 2 degrees, nobody will feel it. But in terms of energy, it will reduce around to 10% of the energy bill. So it's very important to do that. On the other hand, we have the setback temperature. So, for example, in this room, if we all leave this room, of course, the HVAC system is sized to get the full occupancy of this room. But if we leave, changing the set point temperature from 25, for example, to 28, and we go back again from a coffee break or something, changing this temperature has also a great benefit, around to 5 to 7% reduction in the energy bill, of course. And this, by the way, this act has no initial cost. It's a free initial cost, and it will get this operational reduction.
Thank you. I think we all, as citizens, have to be very conscious about energy expenditures more and more nowadays. So it's a conceptual thing, but we have to be more careful about it more and more. Other questions? Yes. So Martin, I knew you. Please, if you could state your name.
Hello. Thank you for this presentation. My name is Rayyan Madad. I'm a master's student in energy studies. I just wanted to ask you, why did you choose the evacuated tube solar collector specifically?
Okay. In fact, I have done this study on 3 solar collectors, the flat plate, the evacuated tube, and the concentrated solar panels. The flat plate has mainly a very low temperature, supply temperature, reaching maximum of 60%, 60 degrees, 70 degrees. So if you are going to this type of solar panels, you need to go to the adsorption chiller. Adsorption chiller is still in progress in its manufacturer way, but and it's